Hello, this is the pre-lecture video for Chapter 4, Part 2. Topics today include oxidation reduction reactions, solution concentration, and titrations. I have a recommendation for everybody. I'm not entirely sure how you've been watching these videos, if you just kind of pull them up on YouTube and watch, but something I might recommend is going to Carmen and downloading the slides for this lecture, loading those up so that you can listen to the audio of this presentation and then maybe make your own notes as you proceed through the chapter. Just kind of a recommendation that might be useful for some of you guys. Of course, if you just want to watch a video, that's fine too. Okay, so one of the topics of today is oxidation reduction reactions. This is the main topic of section 4.4. The idea of these reactions are some reactions occur where some atom or substance will lose electrons. That's a substance called oxidation. Other substances will gain those electrons that are lost. That's called reduction. So oxidation reduction reactions are those types of reactions where maybe something like calcium is oxidized. It will lose electrons to form calcium 2+. So the difference between calcium and calcium 2+ is 2 electrons were lost off of the calcium. Maybe the oxygen picks those up. If O2 gas picks those electrons up, the O2 bond breaks and then we form O2- ions in their place. So you can imagine one calcium atom losing 2 electrons to form the 2+ cation, and then one of the oxygen atoms in O2 picking up 2 electrons to form O2 with the 2- charge. Now for writing this reaction out, we might write calcium solid plus O2 forming calcium oxide. If we want to balance this reaction, we're going to need 2 calciums on the reactant side to react with an O2 gas to form the 2 calcium oxides that we need to put the reaction into balance. Now what we're really balancing here as well is that we're going to need 2 calciums to lose 4 total electrons, and then the 2 oxygen atoms will each gain 2 electrons. And so this is an oxidation reduction reaction. Now substances are not just spontaneously losing electrons without there being something to gain them, and vice versa. You can't gain electrons out of midair. So these reactions cannot occur without each other. They have to occur in tandem. That's why we call these types of reactions oxidation reduction reactions, or sometimes for short just a simple redox reaction. Now, one of the ways we can try to determine if such a reaction occurs is to come up with a bookkeeping system for electrons in charge in reactions. That's through a system known as the oxidation number system. So this system will help us to determine if an oxidation reduction reaction has occurred. So we can find a way to assign oxidation numbers to elements in neutral compounds or in ions. This is a bookkeeping method. It's not exactly always the case that the oxidation number is the actual charge of an atom in a compound. And we'll go through some examples where that is the case, and then we'll go through some examples where that actually is not the case. And we'll try to understand what exactly these rules are supposed to tell us in the first place. It's really a bookkeeping system so we can understand when these types of reactions are occurring. So the sum of all of the oxidation numbers of an atom, the sum of all the oxidation numbers of all the atoms in a compound must equal the charge of that compound. Let's look at a really simple example and keep this simple to start. Let's look at CaCl2. So the CaCl2, the oxidation number of calcium will be its charge. It's the calcium 2+ ion, and each chloride will be its charge -1. So in this case, the oxidation numbers are exactly equal to the charges of these atomic ions within this compound. If we look at a slightly different example, if we were to look at, let's say, for example, calcium sulfate. Now, one of our rules for oxygen we'll see in a moment is that usually its oxidation number is -2, and it is in this compound. And so if we have a total charge of -8, or a total of the oxidation numbers of the oxygens is -8, the calciums are a +2, so what does sulfur have to be such that the overall charge of calcium sulfate is worked out to be 0? It's a neutral compound. So that means the oxidation number of sulfur has to be +6. So we can do 2 + 6 is 8 minus each of those oxygens times -2 to give us the overall charge on that compound to be 0. And so that's how we can work out the oxidation number of sulfur is 6, calcium 2, and oxygen -2. So my system, and the book uses this as well, or that we're going to write the oxidation numbers up on top of the compound, And then we might do some math below to balance them out. So the oxidation number, these are a per atom. So -2 per oxygen. The math, we have to account for all the atoms down below and then balance out to equal the charge. And we'll see a lot of examples as we continue along in this topic. So there are some rules for assigning oxidation numbers. Let's take a look at a few of these. So atomic ions have oxidation numbers equal to their charge. So that's very easy for atomic ions. For oxygen, its basic rule is that it's -2 with a couple of exceptions. Two of the exceptions we've talked about already in class. Peroxides and superoxides exist for some alkali and alkaline metals. And that's it. We don't see these forming with aluminum or transition metals. So if we look at a quick example, we could have calcium O or CaO2 for calcium. And so this would be calcium oxide from our naming. It's a Ca2 plus 2 minus. Oxidation number of oxygen here is the ordinary oxide ion, 2 minus. And then in this case here, this is calcium 2 plus with an O2 2 minus for the entire 2 oxygens. So each oxygen must have an oxidation number of just -1. So the -1 oxidation number is the oxidation number of oxygen in peroxide. Now KO2 is the formula of potassium superoxide, K plus O2 minus. Each of the oxygens actually has a fractional oxidation number of -1/2. So the oxidation number of oxygen in potassium oxide is -1/2. So that's the case for all superoxides. Now we can tell if we have a peroxide or superoxide just from seeing the formula, and then knowing that the charge of the alkali or alkaline is either a +1 or a +2 for those elements. Another exception for oxygen are compounds with fluorine. Not very common compounds, but one such compound is OF2. Now our rule for fluorine is that it's always -1. So fluorine is always -1. That means oxygen has to go positive here. We have a total of -2 for the 2 fluorines, so we have a +2 oxygen in the case of the compound OF2. Now you've probably never heard of that compound. It's not a very common compound, but some of these compounds do exist, and we like to be able to assign their oxidation numbers accordingly. Now the idea here, if you know what electronegativity is, then you know that fluorine is the most electronegative atom on the periodic table. Now that's a topic from chapter 8 that we'll talk about later in the class, but the electronegativity of fluorine means that it's the atom that wants electrons the most. And the desire for electrons, that's where you get your negative charge from. That's where fluorine is the one that's going to go negative and have the negative oxidation number in favor of oxygen, in this case, having the positive oxidation number. Now, if you look at OF2, it's our first example here today of a molecular compound where this is the type of compound where the charges are not exactly equal to the oxidation number of the atoms. So in molecular compounds, this happens a lot. We assign an oxidation number, but it's not the true charge of the atom in the real molecule. OF2 is not an ionic compound, so oxygen really doesn't have a +2 charge in oxygen, but the idea here is that oxygen should be the atom that bears a positive charge in the compound, and fluorine should be the atom that bears the negative charge. Now in the case of hydrogen, usually +1 in the case of molecular compounds, and then -1 in the case of ionic compounds. This is really easy to tell the difference. Let's do 2 quick examples of this one. So we have water. So water, our rule for oxygen should be -2. And what we're thinking here, is it a peroxide or superoxide? I don't see 2 oxygens, so that doesn't make any sense. It's not a compound with fluorine, so that doesn't make any sense. So oxygen has to be a regular -2. And so then each of the hydrogens has to have a +2, so each hydrogen's oxidation number here would be +1. So that's the charge of H, or the oxidation number of H in water. No, of course, H really doesn't have a +1 charge in water. No, it doesn't really have a charge of -2. But in the real case of water, oxygen should bear the negative charge, hydrogen should bear the positive charge. That's why we were writing the structures of the dissolution of NaCl. Remember this, where we were writing the sodium cation was being surrounded by the oxygen atom in water because it bears the negative charge, and then the chloride ion was being surrounded by the hydrogens in water because it bears the positive charge and then is attracted to that negative charge and the Cl minus ion. So when we were trying to understand solution processes early in chapter 4, we were taking advantage of this idea of the charges of the O and the H in water. Now contrast that with something like sodium hydride. Sodium hydride has a formula of NaH. Sodium's always +1. This is an ionic compound, metal, non-metal, so H goes to -1. So hydrogen -1 in the case of compounds with metals, for ionic compounds, +1 with non-metals in molecular compounds. Now all other atoms we're going to figure out just by simple deduction. So we're going to try to deduce the other atoms' oxidation numbers from the ones that we've set rules for, and then just by using the idea that we can sum up all the oxidation numbers of all the atoms in the formula to equal the charge on that compound or ion. So let's look at a lot of examples of this concept. Okay, so let's just approach all of these examples here. This might take a few moments, but let's take a look here at the first one. So H2O2. So H2O2, we can apply our usual rule for hydrogen. It should be +1 in a case of a nonmetal, so a +2. That means my entire O2 group here has to be a -2. This is hydrogen peroxide, H2O2. So we probably knew the name of this right off the bat and probably could realize that the whole O2 group has to have a -2, so each oxygen's oxidation number is -1. So the charge on O2 is an O2-2-, that's peroxide. And so then this is the molecule of hydrogen peroxide. So it looks with the Lewis structure something like this. So we'll get into Lewis structures later though in chapter 8. Okay, so let's look at OF2. We already looked at that one. That's a +2 for oxygen, -1 for the F. So we look at F, it has to be a -1, O has to be a +2. Calcium hydride, +2 for calcium, and then the hydrogens have to go -1 for each of them. So +2 minus 1 times 2 equals 0. Okay, so that checks out. So CaO2, that's calcium 2+, O2 with an overall 2-, so we get a -1 for each of those oxygens. That's calcium peroxide. ClO3-. Now chlorine, we don't know a rule for chlorine, but I know oxygen's -2 with the exception of its exceptions. This isn't one of the exceptions. Not a peroxide, not a superoxide, not a compound with fluorine. So now we do our math here. We get a -6. Now chlorine, we have to set its charge or its oxidation number. I keep saying charge, I should say oxidation number. We have to set its oxidation number to work out to be the charge on this ion of -1. So that's going to be +5. For +5 minus 6 equals +1. So chlorine here is a +5. Iron. If we have iron solid, the charge on an atom without a charge has to be 0. So that would be 0 for the oxidation number of iron without a charge. Of course, iron 2+ would have an oxidation number of 2+. If you have the ion given with a charge, the oxidation number is just the charge. TiO2, the trick here is this can't be a super or a peroxide because those only form with alkali or alkaline metals. And so this has to be an ordinary oxide ion. Times 2 minus 4, so this is titanium plus 4, so this is titanium 4 oxide. KO2 is a +1 minus 1, so that's a potassium superoxide minus a half for the oxidation number on each of the O's in KO2. So superoxides are the only examples that we see here where we get a fractional oxidation number. Br2, elemental form of bromine, has to have an oxidation number of 0. Neither bromine and Br2 could have a charge. Each one has to be the same. The only way for them to be the same and for the molecule to be uncharged is, of course, for each bromine to have an oxidation number of 0. In the case of ClF3, fluorines keep that -1, 3 of them, -3, and then the chlorine goes to +3. Okay, now chlorine's usually -1, but this would be an exception for chlorine. So if you look at like HCl, +1, -1. If we look at CCl4, for example, the chlorines here would be their usual minus, like fluorine. They're going to be minus times 4 minus 4, carbon plus 4. Okay, so it's just when a chlorine is bonded with fluorine or an oxygen, it's not going to have this usual -1 oxidation number. So we saw chlorine up in this example up here with ClO3- was +5 because oxygen state is -2. Last example is K2CR2O7. I'm just going to rewrite that over here to have a bit more room to write. And so for this one, I know potassium is a +1, and I know oxygen has to be a -2. Now the trick here is I got to do the math. So I got to do times 7 for -14, times 2 for +2 for the potassiums. And so chromiums or whatever make the math work to go to a net charge of 0. So the 2 chromiums have to have a total oxidation number of +12. Divide by the 2 of them, goes to +6 overall. Okay, so we have to account for all of the atoms in the arithmetic. So I have to account for the 2 potassiums, the 2 chromiums, and the 7 oxygens. So 2 plus 12 is 14, minus 14 is 0. So these are a few examples. There's a lot more in the book, but hopefully these examples take us through a lot of the nuances of the rules. So now let's look at an example of a redox reaction here. So we have magnesium dissolving in HCl. Now, when magnesium dissolves in HCl, it's forming magnesium 2+. Now, where are the electrons going? The electrons are actually going to the H+ ions, where each one can pick up an electron, form an H, and then bond with another H to make an H2 molecule. So hydrogen gas is actually evolving from this reaction here. So if we want to write our reaction, magnesium solid is reacting with HCl, AQ, to form Mg2+. That's going to pair up with the chloride ions. So MgCl2, AQ. And then the H pluses are forming H2 molecules. So we get H2 gas that evolves from this reaction. It bubbles away. So we're going to take 2 HCl's to give us our 2 chlorines in the product, and then the H2 gas. So magnesium is losing 2 electrons. So we can look at magnesium here and see it's losing electrons. That's oxidation. So magnesium is oxidized. And then the HCl, or really just the H in the HCl. So the hydrogen in HCl is reduced. It gains those electrons. So it's reduced to H2, and then Mg is oxidized to Mg2+. Okay, so a lot of cases, a lot of reactions, we may want to look at a reaction and identify which atoms are oxidized, which atoms are reduced. Chlorine is unchanged. So chlorine remains as Cl-, so it's unchanged during this redox reaction. Now we see our activity series. Now what this activity series is showing us is that metals have a sort of variability on their likeliness of being of having an electron lost or multiple electrons lost to form their charge state. So this is looking at the ease of oxidation. The elements at the top, lithium, potassium, barium, calcium, sodium, these are metals that rarely would you encounter the metal in nature. You'd more likely encounter the cation of the metal in nature because the cations are, in a way, more stable. So the metals at the top of this chart have a higher likeliness of being oxidized and then existing in that oxidized state, existing as their cations. The elements at the bottom of the chart, like if you look at copper, silver, mercury, platinum, gold, these are our precious metals. These are the metals that remain as metals even if they come in contact with acid solution, even if they come in contact with water. All different kinds of things, they stay as metals. So these are our precious metals, which is good because they tend to stay in their metallic form. That's why they are our precious metals. And so we can use this activity series to predict when reactions can occur and when they may not occur. So imagine, I'm just going to pick a couple examples out here. So if we were to take aluminum solid and then try to mix that with, let's say, cobalt nitrate. So that's cobalt 2+. Does a reaction occur? If a reaction occurs, you're going to imagine cobalt going to cobalt solid. So you're going to imagine cobalt solid forming, and then Al3+ forming in its place. And so Al3+ forming, picking up the nitrates. If this is going to react, we can even balance this out. It's going to actually form with 3 nitrates to form Al3+. Cobalt 2+ is what is here, cobalt 0 and aluminum 0. And so if we want to put this into balance, if this reaction were to occur, we're going to need 2 cobalts here, and then we're actually going to need 2 aluminums here to get 6 total nitrates. So we're actually going to need 3 cobalts, and then 2 aluminums. But it's a tricky balancing, but we get it balanced. But here's the kicker. Does the reaction actually occur? Does aluminum dissolve in cobalt and nitrate solution, and then does cobalt solid form in its place? The answer is yes, because what we want to compare is the activity of this metal versus this metal. We want to compare aluminum solid versus cobalt solid. And we see that aluminum is more reactive, it's more active, it's higher on the chart, it's more likely to want to exist in its charged state than cobalt is. Okay, so what we do is we write the reaction out, consider the 2 solids that are reacting in the problem, and try to figure out, do we have the more reactive solid reacting? If so, then we should produce the lesser reactive metal in its place. So this reaction should occur and should take place. Now, if you imagine trying to do the opposite, if you imagine taking, okay, let's take some cobalt and see if it would dissolve in an aluminum nitrate solution. So this is exactly the opposite. So I'm taking cobalt solid and trying to dissolve it in aluminum nitrate. And so this reaction here would simply form aluminum solid if it were to occur, plus cobalt nitrate, CONO32, and of course the balancing would be the same, so we need 2 and 2, and then 3 and 3. So does the opposite reaction occur? So cobalt solid, aluminum solid. Cobalt solid is now less reactive than aluminum solid. So how is something that's less reactive going to react to produce something that's more reactive? That doesn't make very much sense. So this reaction here cannot occur, so this would result in no reaction, whereas the opposite reaction of aluminum and cobalt nitrate being mixed together would lead to a reaction taking place. So there's a lot of examples you could look at here using this activity series to help us predict when reactions can occur and when they can occur in the case of redox reactions. So that wraps up mostly section 4.4. We're going to head into section 4.5 here. So let's talk about molarity. So molarity is a concentration unit. It describes the moles of solute divided by the volume of solution in liters. Now the way this might work is you might imagine taking something like CaCl2 and then dissolving that to a certain quantity of water. And as you add the water, the calcium chloride dissolves, and so maybe you use a flask where you figure out precisely how much total solution you end up with once these 2 substances are mixing together. So oftentimes you might use a volumetric flask, which I'll draw a crappy one, so I'm not a very good artist. But a volumetric flask is calibrated to contain a certain volume of liquid. Let's say we have a 100 milliliter volumetric flask. We add some calcium chloride, we weigh it out, we figure out how much we're adding so we can calculate the moles of the solute very easily, and then we fill it to the line with water. So we put some solid in here, fill it to the line with water, and make sure that the compound's completely dissolved as we add that last drop of liquid to hit that meniscus on the line in our container. And so then we don't know exactly how much water we had to add. Maybe it was exactly 100.0 milliliters, but probably not. But what we do know is that the volume of that solution would be 0.1000 liters. So we measure out the volume of that solution. Now the utility here is that if you know the molarity of a solution and you use a certain quantity of the solution, then you can very easily calculate the amount of solute that you would be adding or using within that volume. So let's take a look at a couple examples here. So what is the concentration or molarity if we were to take 0.250 moles of sodium hydroxide and dissolve that in 200.0 milliliters of total solution? This is very easy. So to calculate the molarity, we would just take the moles of solute divide by the volume in liters. So we can work that out. So that's 0.25 divided by 0.2. That is 1.25 moles per liter. Now I can write that as 1.25 big M, and where the big M equals a mole per liter. Okay, so it's moles of sodium hydroxide per liters of solution. Now how many moles of sodium hydroxide are present in 37.5 milliliters of this 1.25 mole per liter solution. So we can calculate the number of moles. If we were to take a quantity of this solution, let's convert that very quickly into liters, 0.0375 liters. So I can multiply that by 1.25 m, but I'm never going to write m in a problem. You guys might, but I'm not going to. I'm going to write mole per liter. Mole of sodium hydroxide per liter of solution. So I'm using 37.5 milliliters or 0.0375 liters of the solution. So the volume cancels. I get the moles of sodium hydroxide to work out. And so if we do that math, that works out to be equal to 0.0469 moles of sodium hydroxide. Okay, so we can use the molarity unit to help us figure out how much quantity in moles of a solute are contained within a certain volume of solution. Now, we can change the concentration of a solution by adding solvent. So a solution can be diluted by adding just the solvent. So let's take a look here. So the concentration is lower, but the moles of the solute are unchanged. So let's say we take 25.0 milliliters of a 1.0 molar stock solution and put that into a pipette. So we use the pipette very carefully and add that to a new flask. So we add that to a new 250 milliliter volumetric flask. Though the idea of volumetric flask is it's calibrated to hold precisely 250.0 milliliters. And so then we dilute that with water until the solution reaches the calibration mark on the new flask. Now, one of the keys is that it's probably not going to take precisely 225 milliliters of water, because a lot of funny things happen when you mix solutions with pure water. So it may take a little more, it may take a little less, but the key is it doesn't matter how much water exactly you have to add, because we're adding to the total volume of solution to be 250.0 milliliters. And so then we might wonder, well, what's the new concentration? Well, you can think of what you began with in terms of the solution. It was 1.0 molar, and we took 25 mils, and then we diluted it to 250 milliliters. So we can take our initial molarity times our initial volume, and that would tell us the initial number of moles. This is probably a copper solution. It doesn't say within this problem. Copper ions are usually blue in solution, so it's probably some type of copper. So the moles of our solution, we could get that by taking the initial volume times that molarity. I'm actually going to write this out more explicitly and just take a few more moments to show how you could write this out. But you could solve for the number of moles just like we did on the previous page, on the previous problem, by taking the 1.00 mole per liter and multiplying that by 0.025 liters. And so that works out to be equal, of course, to 0.0250 moles of the solute. And so then when we have a new volume of 250 milliliters, so our new molarity would be equal to the moles of our solute, which are unchanging here. We're just adding more solvent, so we still have 0.0250 moles. We now have 0.2500 liters of solution. So if I take 0.025, divide by 0.0025, that works out to be equal, I take 0.025, divide by 0.25, for 0.25 liters, that works out to be 0.100 molar or moles per liter. So I've taken 1.0 molar stock solution and then decreased that concentration by diluting that solution with pure water. Now there's another equation that we can use. The equation is fine, there's nothing wrong with using equations, but sometimes we have to remember how and when and why a particular equation works. An equation that we're going to show works because what it's going to do is show that we're taking the moles of our solute, that's not changing, we're just dividing by our new total solution volume. So let's take a look at that equation. So a dilution equation that we can use is that our MC times our VC, the molarity times the volume, is equal to the number of moles in our concentrated solution. So we take a concentrated solution, take the molarity, mole per liter, times the volume, liters. That gives you the moles in that concentrated solution of the solute. That's not changing when we get to the final diluted volume by just adding the pure water to dilute the mixture. So it's equal to the same number of moles. So then our molarity of our final diluted solution times the volume, the total volume of that diluted solution, must be equal to the molarity of our concentrated solution times the volume of the concentrated solution. So the idea here is your moles, you know that before you dilute the mixture, and you know that moles aren't changing. So, and then of course you know that that's just going to be related to the new molarity times the new volume of the solution. Therefore, the MCVC must be equal to MDVD, where that means the concentrated molarity times the volume of that concentrated solution is equal to the molarity of the diluted solution times the volume, the total volume of the diluted solution. So in the case of the previous problem, we had 1.00 mole per liter to begin with. We had 25 milliliters, and then we diluted that to a total volume of 250 milliliters. And so the diluted molarity would just be 25.0 milliliters times 1 divided by 250 milliliters for 0.100 molar or moles per liter. Okay, so we can calculate it very easily using the equation, but it works for the precise reason that the moles of the solute are not changing during the course of the dilution. Okay, so now this problem is not going to, or this equation doesn't work for every single problem that has a molarity or a volume unit. I see a lot of people try to apply this equation to a titration problem that we're going to talk about in a few moments, and a lot of times the equation is not going to work, and it's because it's not intended to work. This is a dilution equation, works for dilution problems when you're adding water to dilute a concentrated solution into a more dilute solution. Okay, so the final section in this chapter 4 is on stoichiometry of solutions. So we of course know from our work in chapter 3 that you can take mass into moles using molar mass, and you can use the coefficients in a balanced reaction to relate to the moles of a substance as it's reacting in a reaction. So you can relate the moles of a reactant to product or one reactant to another reactant using the coefficients of the balanced reaction. And then you can relate the moles of your new substance to its mass as well. But in chapter 4 here, what we can do is use the molarity unit and volume to also relate to moles. So we're going to see how we can use molarities of substances to relate to the volumes of the substances and the number of moles of a substance as they relate to each other within a reaction. So we're just going to be using volumes and molarity in chapter 4 like we were using masses and molar masses in chapter 3 and solve some very similar looking problems. Let's take a look. Okay, so a titration is an analytical technique where we can use it to help calculate the concentration of a solute in a solution. So imagine you have some type of a solution where you don't know its concentration. Let's say we have an acid solution of an unknown concentration. So we take 20 milliliters using a pipette. So we get 20.0 milliliters of acid, add it to a flask. We add a few drops of an acid-base indicator. We were using an indicator in a lecture example last week where we took a neutral solution, added base, and it turned purple. And then we took that solution and added acid and saw that it very quickly turned red. So we took a solution that was neutral, one color, we made it basic, have hydroxide ions, it was a different color, and then reacted those OH minus ions with H plus, and then we formed an acid solution once we added enough acid, and then the solution turned back to red. So we can change the color of a solution based on whether or not the solution contains acid or base very easily by using an acid-base indicator. So we add an indicator to the solution. Then we take a solution where we know the concentration of sodium hydroxide, and we fill that into a burette. So we can take the burette and add drop-wise to the acid solution. Now, as you're adding, you'll see a pink color. The color of an excess base solution is pink. The acid solution is clear. As you're adding the base, you can see the color for a moment appear purplish or pinkish, and then it dissipates. It's because what you're doing is you're adding sodium hydroxide, but it's very quickly reacting with the H+. So the H+ and the OH- react together to make water. And it just, initially you have a lot of OH-, but not enough OH- to make and react with all the H+. So you have to keep adding and adding and adding the hydroxide solution until the point at which the solution stays pink. At that very instant, you know you've added the precise amount of the base that's needed to react fully with all of the acid. Okay, now it does matter what the acid is. Let's take as an example that this is an HCl solution. And so HCl has to have 1 sodium hydroxide added for every 1 HCl present to make NaCl AQ plus H2O. So HCl plus sodium hydroxide make NaCl plus H2O. Now how can we solve for the amount or the concentration of our original solution? Because usually what we want to do is solve for what is that concentration of the HCl in the original sample. Well, to figure that out, we want to take the moles of HCl in that solution and divide by the volume of that solution. We know that's the 20 milliliter solution, or 0.0200 liters. So what we're going to have to do is figure out, well, how much base does it take precisely? So we might need to figure out what's the concentration of sodium hydroxide, how many milliliters does it take, how many moles of sodium hydroxide had to be added. That tells us how many moles of HCl were present. So we can take the moles of sodium hydroxide, relate that to the moles of HCl, and solve for the moles of HCl to get our molarity of that solution. So a titration technique is use a volume of a standard concentration needed to reach the equivalence point, and then you have an indicator present to indicate that equivalence point, that exact point where you've added the stoichiometric amount of one reactant that's fully needed to react with the reactant in the flask. So the idea is dropwise add one solution to another and have an indicator present so you know the exact moment you get the stoichiometric quantities of the two reactants mixed together. So let's imagine we have HCl being titrated just like the previous example, but instead with calcium hydroxide. So what changes if you use CaOH2? Well, what changes is that 2 HCl's can react with every 1 calcium hydroxide to make CaCl2AQ, and then 2 H2O's. Okay, so we get 2 HCl's that can react with every 1 calcium hydroxide. So we have to take into account that calcium hydroxide is going to be added in, that we only need to add 1 calcium hydroxide for every 2 HCl's present, whereas if we titrate with sodium hydroxide, we need to add 1 to 1. We need to add 1 sodium hydroxide for every 1 and for every 1 HCl. So you can imagine perhaps the case where you're titrating the same solution. Imagine you're titrating the same HCl solution with equal concentrations of either calcium hydroxide or sodium hydroxide. It's going to take half as much of the calcium hydroxide to fully react with all the HCl to lead to that color change as it would if you were to use the exact same concentration of sodium hydroxide. So I think we need to see some problems. So let's see some examples. We'll see a couple on the next page. Okay, so let's take a look at a couple titration examples. So let's say that 20 ml solution of acid that was being titrated on the previous page, let's say that took 33.5 milliliters of 0.100 molar calcium hydroxide to be fully neutralized. Now what this means is we're taking 20 milliliters of HCl, unknown concentration, and then we're taking a burette filled with the calcium hydroxide solution, and we're adding it dropwise until that pink color persists. And we know that's the moment that we've added the right number of moles of calcium hydroxide to balance out the number of moles of HCl, but precisely in the 2 to 1 fashion, that for every 2 HCl's, we're going to need to add 1 calcium hydroxide to form 1 CaCl2 and then 2 waters. Okay, so the way we can work this problem out is to recognize that we're trying to solve for the concentration of HCl in this solution before we even begin adding the calcium hydroxide. So we want to know the concentration of HCl. Well, that's the moles of HCl in that solution divided by the volume of that solution. It's 20 milliliters. So it's 0.0200 liters. Now the moles of HCl, I need to use stoichiometry to figure that out. So the moles of HCl, I can start with the calcium chloride. It's 0.0335 liters of that solution. its concentration was 0.100 moles of CaOH2 per liter of that solution. Volume cancels. And then the stoichiometry is 2 to 1. For every 1 mole of calcium hydroxide, that means that there were 2 moles of HCl present. Okay, so let's talk this through. So we added 0.0335 liters of calcium hydroxide. We used the molarity of that solution. That's the moles of calcium hydroxide that were added. For every 1 mole of calcium hydroxide that had to be added, that means there were 2 moles of HCl present in that solution. So if I want to work out the final molarity here, I'll take the 0.0335 times 0.1, that's the moles of calcium hydroxide, times 2, that's the moles of HCl. Now divide by the volume of HCl in that original solution, 20 milliliters, 0.02 liters. That works out to be 0.335 moles of HCl per liter of solution. Okay, so I'm going to crunch the numbers one more time just because I don't believe them and I may have made a mistake. And I just want to double check my arithmetic. And so I work this out a second time. Yep, that works out. So this solution is 0.335 molar HCl. Okay, now this is a different example down here. So the second example, unrelated to the first, just a new example, says we have 1.25 grams sample of a pure unknown diprotic acid, and that it requires 10.52 milliliters of 0.115 molar KOH to be fully titrated. What is the molecular weight of this acid? Okay, so this particular problem here is telling us that we must have a solid, pure acid. That's true. There's a lot of acids we didn't learn how to name, like involving organic compounds usually. And so you can get a sample, like a pure sample of those compounds, and then like weigh them out very easily. So the thing we may want to try to find here is the molar mass of that acid. So if I said, okay, well, the molar mass of the acid is what we're looking for, the molecular weight. Molar mass is equal to the number of grams of a compound divided by the number of moles of that compound. Right? If we knew the mass of a sample and the moles in the sample, we could figure out the molar mass. So that's the idea that we're using in this problem to solve this problem here. Now the moles, this is the moles of our diprotic acid. Now diprotic acid just means it has 2 H's for every one of the anions. That just means I have like an H2A, so I have 2 hydrogens that are going to react with KOH. And because it's diprotic, means I'm going to need 2 KOHs to fully react here to form K2A. I know A is a 2- since it's a diprotic, so I get K2A. Should be water soluble because all potassium salts are, and then plus 2 waters. Okay, but the key here is this 1:2 ratio of the moles of H2A for KOH. So the way this works is we have an acid present, we're adding KOH, it should react until the KOH persists and we see that color change just like our other titrations. Okay, so the moles of our acid, we can start with the moles of KOH. So we take 0.01052 liters times 0.115 moles of KOH per liter of solution. So we take the volume of KOH times the molarity of KOH, and then we just use the fact that for every 2 moles of KOH that had to be added, that means there was 1 mole of the acid originally present. Okay, so if I take 0.01052 times 0.115 and then divide that by 2, that's the moles of the acid in that original 1.25 gram sample. So then I take my 1.25 gram sample, divide by the number of moles, that gives me a molar mass. Now I'll be honest, I just made these numbers up and they're not very sensible, but the molar mass works out to be equal to be 2,066 grams per mole. And of course that'd be 2,066 AMU for the atomic weight or the molecular weight of this acid in AMU. So 2066 grams per mole, molar mass. If you want the molecular weight, usually an AMU. 2066, of course, AMU. Okay, so two, I think, tricky problems on titrations, but two very approachable problems if we think about what it is we're trying to solve for. If we want to solve for an unknown concentration, start with what it is you want to find. The moles of that substance divide by the volume of the solution. And usually you're given the volume of the solution, and we just have to use stoichiometry to figure out the moles of the acid from the moles of the base that had to be added to fully react with it. Likewise, we have another acid-base reaction. The whole word here that's really important is neutralized. That an acid and a base will react together until the acid and the base have fully reacted together such that all of the H's have been removed from the acid. So if it's diprotic, both H's come off fully, so that we're left with just K2A and the two waters forming. So the idea of neutralization is that all the acid and all the base fully react together, and you can use information about the quantity of base that had to be added so you can solve for the amount of acid that had to be present. Okay, a lot of examples on this topic will be given, in homework problems, so you'll see this type of topic and problem inside and out within the next week or so. All right, well, that wraps up this pre-lecture video. I hope you tune in to more pre-lecture videos, and you have a great day.